So in today's video, we will discuss about the total energy associated with an electron revolving in an orbit. For that, let me consider a circular orbit like this. And we have the center of the orbit or center of the atom, we have a nucleus. And the electron is revolving in this orbit with a radius r. Let its radius be r. Okay. Now we have the charge of the charge of electron. We know it is E. It's actually minus E. Okay. And we know for nucleus, suppose the atomic number of this atom be some Z. We actually have Z number of protons inside the nucleus. Actually, there is protons and neutrons inside the nucleus, but neutrons have no charge. So the charge of the nucleus is actually the total charge of the protons. And we know, and we have total charge of the nucleus. We actually have Z number of protons into charge of a proton. Actually, the charge of electron and charge of proton have same magnitude but opposite sign. So the charge of nucleus is actually Ze. Let's take this as Q1 and take this as Q2. And the first point is, for any rotational motion, the centripetal force is the force that drives a particle in circular motion. So, which means for the circular motion to happen, there should be a centripetal force. And we have the centripetal force. Let's take that as Fc equal to mass of the electron into square of the velocity of electron divided by the radius, this length. Okay. And we have one more force called the electrostatic force. See, these are two different charges and there is always a force between these two charges called the electrostatic force or the Coulomb force. Coulomb's force. Let's represent that as Fe. That is, Coulomb's force is same, otherwise called electrostatic force. And its value is 1 by 4 pi epsilon 0 Q1 Q2. Here actually it is Q1 Q2 divided by square of the distance between the charges. So Fe will be 1 by 4 pi epsilon 0. Q1 is Ze. Ze into Q2 is minus E divided by r square, the square of the distance between the charges. Simplifying, we'll get F is equal to, you can take this minus to the left, so it will be 1 by 4 pi epsilon 0 Ze square divided by r square. Okay, let's call this as equation number 1 and let's call this as equation number 2. And we know this centripetal force, some other force must provide the centripetal force, otherwise rotation won't happen. So this time, in this case, this centripetal force is provided by the electrostatic force. So their magnitude must be equal. That is, the magnitude of the centripetal force must be equal to magnitude of the electrostatic force. So we can write mv square divided by r equal to, you don't have to take the minus sign since magnitude is always positive. So 1 by 4 pi epsilon 0 Ze square divided by r square. You can cancel one of the r. So the final expression here will be, that is r is equal to, or you can multiply this r to the left, so it will be mv square r equal to Z e square divided by 4 pi epsilon 0 implies r equal to z e square divided by 4 pi epsilon 0 mv square. Okay, call that as equation number 3. And we know from the Bohr's quantization principle, that is from Bohr's quantization principle, see this electron take the orbit, the electron revolves only in the orbit where the angular momentum, that is angular momentum, is an integral multiple of h by 2 pi. That's actually Bohr's quantization principle. Here L is the angular momentum. Angular momentum, we already discussed about the derivation of this one. If you want to know about this equation, you can always go back and check the video. Okay, the heading, the title is actually Bohr's quantization principle, the derivation of Bohr's quantization principle. So we have L equal to nh by 2 pi. Also, for circular motion, L is actually mvr, the linear momentum into radius, equal to nh by 2 pi. See, this L is mvr. And we have V is equal to nh by 2 pi mr, taking this m and r to the right. So this is another expression. Sorry, this is the expression for velocity. Call that as equation number 4. Now we want to substitute this value in this equation. We have a v square in here. Instead of this v, I'm putting this value in here. Okay, so what I'll get? So substituting 4 in 3, we have r equal to z e square by 4 pi epsilon 0 m into, instead of v, I'm plugging this value. So nh by 2 pi mr square. Okay, so this will be r equal to z e square divided by 4 pi epsilon 0 m. I can square this, all these values, that is n square by h square divided by 4 pi square m square r square. Okay, I can cancel this 4 from here itself. One of the pi and one of the m will also get cancelled. So this will be r equal to z e square. See, the remaining pi, m and r square will move up. This will go to the numerator. So pi m r square divided by, here it will be epsilon 0 n square h square. Okay, now I can cancel this r and this r, one of the r. Okay, actually there is an r square in here and there is only one r here. So the remaining value on the left side will be 1. So I'll get the final expression. I can take this value to the left, that is epsilon 0 n square h square equal to z e square pi m r. Okay. Now the r will be r equal to, taking these values to the left, it will be epsilon 0 n square h square divided by z e square z square pi into m. Okay, this is the expression for the radius. Okay, let's call that as equation number 5. Okay, so this is expression for the radius. Now we have kinetic energy. The expression for kinetic energy is equal to half mv square. And we have mv square. See, that's the relation we took earlier. Let me write that again. We have the centripetal force mv square by r equal to, we already written this, okay, equal to electrostatic force or Coulomb's force, that is 1 by 4 pi epsilon 0 z e square divided by r square. This is the first, this is the from this equation we started all this derivation, okay, that is Fc equal to Fe, modulus of Fc equal to Fe. Okay, here you can cancel this r, so mv square, so I'm plugging this value for the kinetic energy, okay, for the mv square in the kinetic energy. So kinetic energy is equal to half mv square is this value, 1 by 4 pi epsilon 0 z e square divided by r. We have r from the equation 5, that is epsilon 0 n square h square divided by z e square pi m. Clear? See, there is an r in here and I'm substituting this value in here, okay. So this is the value of r, okay. I just plugged it in here, okay, this value in here. Now I have to simplify this expression, okay. So the kinetic energy Ke is equal to, see, this 2, I'm just multiplying this 2 with 4 pi epsilon 0. So 1 by 8 pi epsilon 0. In the numerator we have z e square. Also this denominator, the denominator of this term will go to the numerator. So z e square pi m divided by, we have epsilon 0 n square h square. Simplifying this, you will get Ke is equal to 1 by, or z into z is z square, e square into e square is e raised to 4 pi m divided by 8 pi, this is epsilon 0 square n square h square. See, this, you can cancel this pi also. So the kinetic energy is equal to z square e raised to 4 m divided by 8 epsilon 0 square n square h square. Okay, this is the expression for kinetic energy. Call that as equation number 6. Now we need to find the expression for the potential energy. Before that, let me write the expression for that radius again, because I just erased that. That is, we have the radius, we already derived this, r is equal to epsilon 0 n square h square divided by pi z e square m. Okay. Again, let me draw that orbital again. We have the nucleus Ze and we have an electron E, and the distance between electron, the charge of the electron is minus E. This is the radius. Okay. Now the potential energy between these two charges, we have the general expression, potential energy of system of two charges. We have 1 by 4 pi epsilon 0 Q1 Q2 divided by R12. This is the general expression. Therefore, Pe is equal to 1 by 4 pi epsilon 0. Here Q1 is Ze into Q2 is minus E divided by R12 is R. Okay, so the potential energy will be, let me take this minus to the left. So minus Ze square divided by 4 pi epsilon 0. Now let me plug in this value for r. That is epsilon 0 n square h square divided by pi z e square m. You can cancel this pi and this term will move to the numerator. So the potential energy will be minus z e square into z e square m divided by 4 epsilon 0 square n square h square. Again, on simplifying this, let me erase this. We'll get the potential energy P is equal to minus z into z is z square e raised to 4 m, that is e square into e square is e raised to 4, divided by 4 epsilon 0 n square h square. So this is the expression for the potential energy. Now we have the total energy. Total energy is always the sum of the potential and kinetic energies. So the total energy, usually considered as energy in the nth orbit, is the sum of kinetic energy and potential energy. So energy in the nth orbit is equal to, we have kinetic energy z square e raised to 4 m divided by 8. See, there is an epsilon square in here. Okay. 8 epsilon 0 square n square h square plus potential energy is minus z square e raised to 4 m divided by 4 epsilon 0 square n square h square. Okay, we have to make the make the denominator same. So what I'm doing is I'm multiplying it 2 on the numerator and the denominator of the second expression. So the energy En will be, now this 2 and 4 will get, let me write that again. Okay, z square e raised to 4 m divided by 8 epsilon 0 square n square h square minus, this plus and minus will become minus 2 z square e raised to 4 m divided by 8 epsilon 0 square n square h square. So this is equal to, see, this term remains the same. Okay, so minus 2, here there will be 1. Minus 2 plus 1 is minus 1. Okay, so minus z square e raised to 4 m, because the denominator remains the same. Okay, 8 epsilon 0 square n square h square. Therefore, En equal to, we have the final expression En equal to minus z square e raised to 4 m divided by, this is z square e raised to 4 m by 8 epsilon 0 n square h square. Okay, so this is equal to, let me rearrange this expression. So this will be minus z square e raised to 4 m divided by 8 epsilon 0 h square into 1 by n square. Okay, so we can clearly confirm that energy in the nth orbit is inversely proportional to square of the orbit. Okay, now we can simplify this constant. Okay, see, this is a constant, that's why I took En proportional to n square. Now we have energy in the nth orbit En is equal to minus, see, for hydrogen we have Z equal to 1. For hydrogen we have Z is equal to 1. So 1 square into charge of electron is actually 1.6 into 10 raised to minus 19 coulomb. 19 raised to 4 into mass of electron is actually 9.1 into 10 raised to minus 31 divided by, so we have this 8 as 8 itself. Epsilon is equal to, we have the epsilon 0 actually means the permittivity of free space. Its value is 8.85 into 10 raised to minus 12 square into n square, into h square is, h is actually Planck's constant. Its value is 6.636 into 10 raised to minus 34 square into 1 by n square. So this will be approximately En is equal to, that is total energy is equal to, on simplifying this you will get minus 2.167 into 10 raised to minus 18 by n square, this n square joule. Okay, so this is the total energy in terms of joule, or 2.16 into 10 raised to minus 18. When you convert this into electron volt, you have to divide it with 1.6 into 10 raised to minus 19. This will be approximately 13.6 electron volt. So we generally write this expression in terms of electron volt. So the final expression of the energy in the nth orbit is equal to En equal to minus 13.6 by n square electron volt. Clear? Now we need to find the Rydberg's equation or Rydberg's formula. That's actually simple. Let me erase all this. We found out energy in the nth orbit is equal to minus 13.6 by n square electron volt. Okay. Now suppose we have two energy levels. Let this be the initial energy level, initial orbit, and this is the final orbit. And when an electron moves from the higher orbit to lower orbit, it will release certain spectrum. Okay, and we can find the wavelength of the spectrum using the Rydberg's equation. And we have the energy in the initial orbit is actually minus 13.6 divided by ni square from this equation, and energy in the final orbit nf stands for the final orbit, and ni the initial orbit, minus 13.6 divided by nf square. Okay, so the change in energy delta E is equal to, we have the initial energy minus the final energy. So that will be minus 13.6 divided, this is in electron volts, okay, by ni square minus 13.6 divided by nf square. So this will become plus, so that 13.6 by this term will come first, nf square minus 13.6 divided by ni square. You can take this 13.6 outside by into 1 by nf square minus 1 by ni square. Okay, electron volt. You better convert this electron volt into joule. So this will be 13.6 1 by nf square minus 1 by ni square into 1 electron volt is actually 1.6 into 10 raised to minus 19 joule, because we are going to take the speed of light. All these are in SI system, so we have to take the joule. Okay, now so this is delta E, and we have delta E is actually from Planck's quantum theory. Energy are always transmitted in form of packets. So the change in energy delta is equal to hc by lambda, where lambda is the wavelength, h we know it's Planck's constant, c the speed of light. So I can put in hc by lambda instead of delta E. So hc by lambda is equal to 13.6 into, this term is 1.6 into 10 raised to minus 19 into 1 by nf square minus 1 by ni square. Okay, so this will be 1 by lambda equal to 13.6 into 1.6 into 10 raised to minus 19 divided by hc. Here h is see, this hc will move to here in the denominator. So the value of h is 6.636 into 10 raised to minus 34 into c is actually speed of light, 3 into 10 raised to 8 into 1 by nf square minus 1 by ni square. Okay, so simplifying this, you will get approximately 1 by lambda, which is actually equal to lambda bar, the wave number. This is called wave number, equal to, this is approximately 1.097 into 10 raised to 7 into 1 by nf square minus 1 by ni square. And this value is called Rydberg's constant, R. So the final expression will be lambda bar, which is equal to 1 by lambda, reciprocal of wavelength, is equal to Rydberg's constant into 1 by nf square minus 1 by ni square. Clear? So this is the Rydberg's equation or Rydberg's formula.